Welcome all. In the last lecture, we were discussing the Foster 1 and Foster 2 form of synthesis, and we will continue our discussion in this lecture too. So in this lecture, we will discuss some numericals on Foster 1 and Foster 2 form. Let us consider this numerical. We are provided a impedance function which is equal to 2 times s plus 1 into s plus 3 whole divided by s plus 2 and s plus 4, and we are required to synthesize the network. The first step in synthesis is to identify the network function, that is whether it is a LC function, RC function or RL function, and we'll check them using the properties of LC, RC and RL functions. In LC functions, the network function is the ratio of even to odd polynomials, but as here I can see that it will be a general polynomial, that is it will not be neither even nor odd, and this will not be neither even nor odd. That means I can say that it is not a LC impedance function. And now I am left with two options: either it will be RC function or an RL function. The distinction between RC and RL function can only be made by knowing the singularity lying nearer to the origin. In case of RL function, singularity lying near the origin was a 0, and in case of RC function, the singularity lying near the origin was a pole. So let us check this one. We have zeros here which are lying at -1 and -3, and we have poles here which are lying at -2 and -4, and as clearly seen that this -1 is much closer to the origin, hence I will say the given function is a RL impedance function. That means now I will synthesize it using resistance and inductor. I will use the method Foster 1 form, which disintegrates the given network function into smaller order network function, that is Zs will be equal to Z1s plus Z2s plus Z3s and so on. But if I use partial fraction for the RL impedance function, I already know that the residues of this RL function are real and negative. That means if I perform the partial fraction with this, I will come up with Z1s minus Z2s minus Z3s and so on. That means I cannot perform the partial fraction directly with this Zs. So what do I need to do? I need to divide this Zs by s, and we have this property that if the residues of Zs are coming to be real and negative, then we will find Zs by s. Now this will be equal to now the residues of Zs by s will come out to be positive, that is its residues will come out to be positive. Now I can also see that the degree of numerator is less than the degree of denominator, and I can directly apply the partial fraction methods. So applying the partial fraction, I'll get a by s plus b by s plus 2 plus c divided by s plus 4, where a, b and c are the residues. A, b and c are residues. So I can calculate a, b and c using the residue theorem. So a will be equal to given network function times the pole. So I will multiply 2 into s plus 1 into s plus 3 divided by s into s plus 2 into s plus 4 with s, and I will substitute s equal to 0. So I will get this s and this s will cancel out, and on substituting s equal to 0, I will get 2 into 1 into 3 divided by 2 into 4, and this will be equal to 3 by 4. Similarly, we will calculate the value of b. B will be equal to the function multiplied with s plus 2. The function is now multiplied with s plus 2 and substituted s equal to minus 2. This will give, now I will substitute the value of s, which is s minus 2, s equal to minus 2, and I will get 2 into minus 1, 1 whole divided by minus 2 into 2, and this will come out to be 1 by 2. Similarly, calculating the value of c, c will be equal to function multiplied with s plus 4. So I will have this s plus 4 will cancel out with this s plus 4, and I will substitute s equal to minus 4 in the remaining factors. I will get 2 into minus 3 into minus 1 divided by minus 4 into minus 2, and if I solve it, I will get this to be 3 by 4. So now I have the values of a, b and c. I will substitute them there. That means I will get Zs by s to be equal to 3 by 4 divided by s plus 1 by 2 divided by s plus 2 plus 3 by 4 divided by s plus 4. So Zs can be written as, Zs will be equal to 3 by 4 plus 1 by 2s divided by s plus 2 plus 3 by 4s divided by s plus 4. I have taken this s this side, that is multiplying this s with this term and this term. Multiplying with this term will give 3 by 4. Multiplying with this term will give 1 by 2s divided by s plus 2, and multiplying with this term will give 3 by 4s divided by s plus 4. Now this is the disintegrated form of the given network function, as all the terms are of either 1 order or 0 order, and I already know that this will be a RL function. So the possible network functions could be, if it is a R, then its z of s will be equal to R. If it is L, then its z of s will be equal to Ls, and if it is the parallel combination of R and L, then this Zs will be equal to R into Ls divided by R plus Ls. This can further be simplified as R into Ls divided by, taking L common, I will get S plus R by L, that is making the coefficient of S to be 1. Further solving, I will get Rs divided by S plus R by L. Now comparing these network functions with them, I will get that this 3 by 4 resembles this network function. That means this 3 by 4 is nothing but the resistance. So I will write that R naught is equal to 3 by 4. Similarly, if I compare this, then this resembles to this form. So from here I get that R1 equal to 1 by 2 and R by L equal to 2. Now solving this, I will get, say this is R1 by L1. Now solving this, I can write L1 to be equal to 2 divided by L1 to be equal to R1 divided by 2. R1 we already know it is 1 by 2. So L1 will be equal to 1 by 4 Henry. This should be in ohms. This should be in ohms. Similarly, comparing this term with this, I will get that R2 to be equal to 3 by 4 ohm and R by L, R2 by L2 to be equal to 4, or I can write L2 to be equal to R2 by 4. Substituting the value of R2, I will get 3 by 16 Henry. Now we have the values of all the components. Now this network function says that the circuit will be having a resistance connected in series with the parallel combination of R1 and L1. Further, this will be connected in series with the parallel combination of R2 and L2. So the circuit will look something like this. We have a resistance of the value 3 by 4. Now this will be connected in series with the parallel combination of a resistance and an inductor. The resistance will be of 1 by 2 ohm. So I will write 0.5 ohm, and inductor will be of 1 by 4 ohm. So I will write 0.25 Henry. Sorry, this should be 0.25 Henry. Further, this will be connected in series with the parallel combination of another resistance and an inductor. Now this resistance will further be 3 by 4 ohms, 3 by 4 ohms, or I can write 0.75 ohm, and this will be 3 by 16 Henry. And completing the circuit. So if seen from this side, I will get this ZS. So this is the Foster 1 realization of the given network function ZS. Let us discuss the next numerical. We are given this ZS, which is equal to S square plus 5S plus 4 divided by S square plus 2S, and we are required to synthesize the network using Foster 2 form. Foster 2 form. Let's start. The first step in the synthesis is to identify whether the given function is a LC function, RC function, or RL function. As we can clearly see, it is neither even nor odd, same as with this denominator function. It is neither even nor odd, hence it cannot be a LC function. So it must be either a RL function or RC function. To identify whether it is a RL and RC function, we must find out its poles and zeros. So let us factorize it. We have ZS, and this can be factorized as S plus 1 into S plus 4 whole divided by, I can take out S common from here, S into S plus 2. So the zeros are lying at -1 and -4, and the poles are lying at S equal to 0 and -2. Now from this I can clearly see that it has a pole lying at the origin, or that is, it has a pole which is nearer to the origin. So if any function has a pole nearer to the origin, then it surely must be a RC function. So that means we are given RC impedance function, and we have to realize this using the Foster 2 form. And we already know that this Foster 2 form is also called admittance form or parallel form, because this gives a network in the parallel form, and for the synthesis it uses admittance function. But we are given with the Z. So let us first convert it into admittance function. We have y of s, which will be equal to s square plus 2s whole divided by s square plus 5s plus 4, or in the factored form I can write it to be s into s plus 2 whole divided by s plus 1 into s plus 4. Now to synthesize this using the Foster-2 form, it is required to disintegrate or decompose the given network function into smaller network functions. To do so, we will apply partial fraction method. Now if I divide or I decompose the given network function into smaller network functions, the residues will come out to be negative because it is a RC admittance function. It is now a YRC function, and we already know that YRC function have real and negative residues. Real and negative residues. So to make the residues positive, we will calculate y of s by s, and this will be equal to s plus 2 divided by s plus 1 into s plus 4. That is, dividing this by s, I will get this. Now using the partial fraction, I can write this to be a divided by s plus 1 plus b divided by s plus 4, where a and b are the residues of s plus 1 and s plus 4 in the function ys by s. Now let us calculate the value of a and b. A will be equal to multiplying this function with s plus 1, s plus 2 divided by s plus 1 into s plus 4, and multiplying the function with the pole s plus 1 and substituting s equal to minus 1. I will get, these two terms will cancel out. I will get s plus 2 divided by s plus 4, s plus 2 divided by s plus 4, and substituting s equal to minus 1. Substituting s equal to minus 1 here will give 1 by 3. So this is the value of a. Similarly, I will calculate the value of b. B will be multiplying this function with s plus 4, that is s plus 2 divided by s plus 1 into s plus 4, multiplying this function with s plus 4 and substituting s equal to minus 4. I will get s plus 2 divided by s plus 1 and substituting s equal to minus 4. After substituting s equal to minus 4 in this expression, I will get minus 2 divided by minus 3, and further solving I will get 2 by 3. So now I have the values of a and b. I can substitute this value here. So y of s by s will be equal to 1 by 3 over s plus 1 plus 2 by 3 divided by s plus 4. Now this implies y of s can be written as 1 by 3 of s divided by s plus 1 plus 2 by 3 of s divided by s plus 4. Now I already know that this function y of s is a YRC function, that is, it can be synthesized using R and C only. So let us see what can be the possible admittances of R and C. If I have a R, then its admittance can be equal to 1 by R. Similarly, if I have a C, then its admittance will be equal to CS. And similarly, if I have a series combination of R and C, then the admittance function will look y of s will be equal to 1 by R into CS divided by 1 by R plus CS. On solving, I will get CS divided by 1 plus RCS. Further solving it, I will get, taking RC common, further simplifying, I will cancel this C with this C, and I will get 1 by R of S divided by S plus 1 by RC. Now I have all the possible network functions. Comparing these network function with them, this is similar to this function and this also is similar to this function. So we will compare both these function with these functions and we will try to get out the values of R and C from these. Comparing this function with this, I will get 1 by R to be equal to 1 by 3 and 1 by RC to be equal to 1. Let me number them R1, R1, C1. So I have the value of 1 by R1. I'll to calculate the value of C1. So C1 will be equal to 1 by R1 and this will be equal to 1 by 3 farad. Similarly, this R1 will be equal to 3 ohm. Now comparing this network function with this, I will get 1 by R2 to be equal to 2 by 3 and 1 by R2C2 to be equal to 4 from here, and I will get C2 to be equal to 1 by 4R2. We have 1 by R2 to be equal to 2 by 3. Substituting the value, I will get 1 by 6 farad. So I have the value of C2. Similarly, I can get the values of R2. This will be 3 by 2 ohms by reversing this. So this circuit would look like Y1 is the series combination of R1 and C1. So I will substitute a R here which is having a value of 3 ohm and a C which is having a value of 1 by 3 farad, connected in series combination of R2 and C2, where R2 is 3 by 2 ohm and C2 is 1 by 6 farad. R2 is 3 by 2 ohm and C2 is 1 by 6 farad. So the network will look something like this. So this is the Foster 2 realization of the network function y of s. So in this lecture we discuss Foster 1 and Foster 2 realization of the network functions. In the upcoming lecture we will discuss the core 1 and core 2 form of realization. Till then, thank you so much for listening.